Welcome back to the deep dive. So if you've been following our work in the identity and security domain, we spent a lot of time defining who can access what.
A lot of time.
We really have. We've been mapping out, that whole permissions landscape with identity and access management, or IAM.
Right, the foundational work, the access control lists, the basic building blocks.
And while that foundation is, it's absolutely essential, it's really only half the story in modern cloud infrastructure, isn't it?
It is. Today, we're sort of leaving that traditional access control behind to move into the deep end. We're shifting the focus entirely.
To what exactly?
We're addressing what is arguably the single most critical advanced phase of enterprise security today, securing the entire deployment pipeline, the secure supply chain.
Okay, that shift is profound. We're changing the question entirely.
We are.
It's no longer just who can access the database. It's more like, is the code running on the database server actually the code we approved?
That's it. And the complexity just jumps significantly there because we have to establish identity, not just for the human or the machine accessing the environment, but for the artifact being deployed, the code itself.
Right. We're talking about integrity, provenance, and deploy time governance.
Exactly. Our target listener today, you, the security engineer, the DevOps professional, you need to move beyond those basic concepts and into the actual technical workflows for making this all happen.
Okay, let's unpack this mission then. We've structured this deep dive around, I think, 4 critical advanced pillars. Is that right?
That's 4 pillars, yeah.
First, we're going to establish the foundational principle of eliminating static risk. Then second, how we enforce code integrity at deploy time. We're calling this the inspection station.
With binary authorization, yeah.
Third, how we manage sensitive runtime needs, the vault for secrets management. And finally, credential zero, which is how our machines operate securely without static credentials, and also how we handle the data they produce, the privacy filter.
And we have to begin with the absolute non-negotiable foundational principle for any expert-level security practice in the cloud.
Before anything else.
Before we even talk about code integrity or runtime secrets, we must eliminate the easiest and honestly the most common vector for credential theft: long-lived credentials.
You are talking, of course, about service account JSON keys.
The boogeyman of cloud security.
They really are.
Yeah.
They're just static files, and their lifecycle management is, it's notoriously difficult. If they're breached, if they're accidentally committed to source control or left in an S3 bucket,
An accessible storage bucket.
they grant access indefinitely, forever. Until someone manually finds them and rotates them, it's a massive unnecessary risk.
They violate the core tenet of zero trust. It's that simple. They create a permanent, hard-to-audit entry point. The most secure solution, the definitive answer for eliminating this risk, is to apply a sweeping organization-level constraint.
Okay, so this is administrative action. Give us the specific constraint.
We are talking about applying the organization policy constraint, constraints IAM.disable service account key creation.
And you apply this where?
At the organization level. This has to be a definitive, top-down policy decision. It says, organization-wide, we will not create these keys. Full stop.
And the value there is it just stops the problem before it can even start.
Exactly. It prevents teams from inadvertently creating a security loophole just because, it was the easiest path to get something deployed.
That sounds like a beautifully simple, sweeping solution.
Yeah.
But we know the reality of enterprise environment.
Right. There's always an exception.
You're going to have that legacy system or a weird third-party application, maybe an old monitoring tool. Something that genuinely requires a static service account key to function because it hasn't adopted modern authentication.
It happens all the time.
So if that strict constraint is enforced organization-wide, how do you handle that specific necessity without just weakening the entire policy for everyone?
This is where operational reality meets security idealism, and you have to handle it surgically. The critical rule is this. You never, ever remove the IAM-DAX disable service account key creation policy organization-wide.
Yep.
Never. Doing so would just expose every single project to the risk, completely violating the security posture you just worked so hard to establish.
So how do we carve out that necessary, least permissive exception?
The recommended practice is to handle it locally and with extreme precision. You maintain the strict enforcement across the organization, but you add a specific organizational policy rule to set IAM.disable service account key creation to off it, but only in the specific project where that third-party app needs the key.
So you need a dedicated, isolated project just for these legacy applications.
That's the best practice, yes.
I have a follow-up question on that surgical approach, though. Doesn't making that exception public knowledge, even if it's contained to one project, increase the chance of, internal abuse in that specific project?
That's a vital pushback. And you're correct. The blast radius is minimized, but the risk still exists inside that one project.
So how do you audit access to that single vulnerable project where static keys can be created?
It has to be treated like a high-risk environment. That specialized project must be tagged with unique metadata and subjected to enhanced logging and monitoring. Specifically, you have to set up an audit sync to track the Create Service Account Key API call.
Just in that project?
Specifically within that project. Any attempt to create a key should trigger a high-priority alert to the security team.
And I assume you lock down the permissions for creating them, too.
Oh, absolutely. The IAM permissions for im.serviceaccountkeys.create within that project should be restricted to an extremely small, highly trusted set of administrators. You need a strong separation of duties. This minimizes who can create them and maximizes visibility on that inevitable exception.
That level of clarity is vital. Okay, so now that we've established our fundamental policy, no static keys with auditable exceptions, let's move to code integrity. Let's move into our inspection station. Binary authorization, or BINAUTH. This is truly one of the technical heavyweights.
It really is.
It feels like the mechanism that separates a basic container deployment from a true enterprise-grade secure supply chain. We're calling it the inspection station because it acts as that final, non-negotiable gatekeeper before code can land in a production environment. To make this whole thing digestible, let's use that airport security analogy we talked about.
The analogy is perfect because it introduces the concept of a chain of trust, which is exactly what BINAUTH enforces. The fundamental security problem it solves is stopping the human element.
What do you mean by that?
It prevents a developer or even a privileged operator who thinks they know better from circumventing the automated testing pipeline.
All your unit tests, security scans, load tests.
All of it. It stops them from pushing unapproved or unverified code directly into production clusters. It enforces the policy at the runtime level, and it doesn't matter what the operator's IAM credentials are.
Let's clearly define the roles in this chain of trust. Lay out the analogy for us.
Okay, so we start with the thing we're trying to secure, the container image. That's the actual software artifact built by your CI/CD pipeline. That is our passenger. It's the unit of deployment that needs verification. It holds all the application code, all the dependencies, everything.
And then we need someone to check the passenger.
Right. Then we have the entity responsible for confirming that the passenger is safe and has completed all the necessary steps. That's the attester.
So in our analogy, the attester is?
The attester is the TSA agent,
The
the trusted authority. In the real world, this is usually your hardened, automated CI/CD, pipeline cloud build, Jenkins, whatever you use.
And its job is to run all the mandated check scans, tests, and so on.
Yes, and critically, to confirm that they all passed successfully.
Okay, so once the TSA agent, the attester, confirms everything is clear, they issue some kind of proof.
That proof is the attestation. And in the analogy, that's the stamped boarding pass.
Stamped boarding pass. I like that.
And it's not just a simple log entry. It's a cryptographically signed JSON web token, a JWT, that is linked irrevocably to the specific image digest.
It's SHA-256 hash.
Exactly, so you can't fake it.
All right, so we have the passenger, the TSA agent, and the stamped boarding pass. What's the last piece?
The last piece is the deployment environment itself, the production cluster. That's the plane. And it has a definitive mandate enforced by the rule, which is the BINAUTH policy.
And this policy says, what?
The policy, which is enforced on the GKE cluster, dictates that the deployment will be blocked. The plane will not take off unless the container image, our passenger, has a valid current digital stamp.
The attestation.
Signed by one of the organization's designated trusted agents, our approved CI/CD attesters. If that stamp is missing, or it's invalid, or it's signed by some unauthorized party, the deployment is blocked instantly.
That really is the moment of truth, isn't it? Even if a developer has the IAM role, the permission, to run kubectl apply.
Doesn't matter.
If the image itself lacks that cryptographically sound attestation, the deployment just fails.
It fails with a binary authorization failed error. You've completely separated access control from integrity control. This is deploy time enforcement at its finest.
And this leads us to the first, most straightforward layer of control, right? Just knowing where the image came from.
That's it. The essential first step for any organization adopting GKE is enabling BINAUTH to enforce basic provenance policies. Before we even get to complex attestation schemes, we just need simple guardrails.
Guardrails.
We have to ensure that only images from approved, centrally managed repositories are used. This prevents a whole host of risks.
Like deploying locally built development images by accident.
Or accidentally introducing untrusted public artifacts from Docker Hub that might contain malware or backdoors.
This is so crucial for preventing what's known as dependency confusion or artifact injection risk.
For sure, where a malicious party tries to trick your pipeline into pulling a rogue image.
So if we're using, say, Artifact Registry as our approved internal image source, how does Binoff lock down GKE to only accept artifacts from there?
You implement a binary authorization policy that relies on a specific whitelist name pattern. So, for example, if your centrally managed registry for production artifacts is at artifactregistry.io altastrat images, your policy is configured to only allow deployments where the image name string exactly matches that pattern.
And this is a crucial intermediate step.
It's a crucial control because it forces every deployed artifact to have passed through your central auditable build system. It minimizes the attack surface and enforces that foundational supply chain control.
And to give that even more depth, we're not just whitelisting the repository.
Yep.
We can get more granular, right, based on namespace or cluster labels.
Absolutely. The policy language is very flexible. You might set up one policy for your development cluster that allows images from a broader set of internal repositories. But the production cluster policy, the plain, that one must have the strictest whitelist. It should only allow images from that final hardened registry path.
So you have a layered approach that scales security appropriately across environments.
Exactly. It's the principle of least privilege, but for the artifacts themselves.
Now let's jump to the full expert level scenario, the one that ties workload identity and binary authorization together.
This is where it gets really powerful.
So the scenario. We have a testing pipeline running automated load tests in a pre-production GKE environment. We only want builds that successfully pass these rigorous tests to proceed to the production GKE environment.
Right.
We need a cryptographically verifiable stamp that proves the load test happened and passed, and that this stamp was created by a trusted identity, all without using any static keys.
This is the pinnacle of the secure supply chain. The enforcement method is configuring that automated build pipeline, which is running inside GKE, as the trusted attester. But the mechanics of how it signs the attestation, that has to follow the highest standard to eliminate any risk of key exposure.
Okay, walk us through the step-by-step secure process for performing that cryptographic signing, keeping in mind our initial directive. No long-lived credentials.
The secure attestation process requires an asymmetry, a public key for verification and a protected private key for signing. First, that private signing key must be stored and managed in a highly secure, hardware-backed location.
Cloud Key Management Service.
KMS.
Cloud Key Management Service.
Yeah?
Cloud KMS. We use an asymmetric P256 key pair specifically for this signing operation. KMS acts as the vault that never ever reveals the private key. It only performs the signing operation internally when you ask it to.
Okay, so the key is secured in KMS. Now, how does the ephemeral GKE pod, the one running the successful load tests, get authorization to use that protected key in KMS?
This is the crucial third step, and it ties right back to Credential Zero. Authentication to KMS for signing the attestation must be done exclusively via workload identity.
So there are no keys stored as Kubernetes secrets.
None. The workflow is precise. First, the GKE pod is assigned a specific Kubernetes service account, a KSA.
Second, a corresponding Google service account, a GSA, is created, and it's granted the necessary IAM role to use the KMS key, specifically the cloudkms.signer or cloudkms.cryptokeysigner on that one specific signing key.
The very least privilege.
Extremely. Third, the KSA and GSA are mapped using the workload identity configuration. This is the bond.
And what happens when the pod actually needs to sign something?
The signing application within the GKE pod requests a token. The pod exchanges its internal KSA identity for temporary ephemeral credentials that are associated with the GSA. Then, using those temporary credentials, the pod sends the image digest and metadata to KMS, which performs the signing operation internally.
And what does the resulting attestation actually contain? It's not just a true-false message, is it?
Not at all. The attestation is structured data. It contains the exact image digest, the SHA-256 hash to timestamp of the verification, the identity of the signer, which is the GSA, and critical metadata about the tests performed.
Like load test XYZ completed successfully.
Exactly. So when the production GKE cluster checks the policy, it's verifying three things. One, that the signature is valid. 2, that the key used belongs to a trusted attester, and 3, that the signature matches the specific image digest being deployed.
So if you tried to deploy a single byte change to the image,
The digest would change and the attestation would instantly become invalid.
that is robust. And if you tried to use a static JSON key stored as a Kubernetes secret to do this,
You're just putting the master key to your attester in an accessible file on the cluster. It completely undermines the entire security model.
you've just traded one security flaw for another.
Right, from the container registry to the Kubernetes secret store, which is often easier to exfiltrate. Workload identity ensures that signing power is tied to the brief, ephemeral execution lifetime of that one authorized pod.
Okay, so before the container image even reaches that inspection station for the final attestation stamp, we need to shift security left. We need to apply checks earlier. What's the preliminary check organizations have to run on the container to make sure it's not, riddled with known issues?
Vulnerability spanning, it's non-negotiable. The recommended security shift left step is using container analysis to automatically scan images for flaws as they're pushed into artifact registry.
And this is checking what exactly?
It scans the operating system layers, your Alpine or Ubuntu-based images, and the application dependencies like Java or Node libraries. It then reports any common vulnerabilities and exposures, CVEs, immediately upon ingestion into the registry.
So it generates a sort of report card on the image's health.
Yeah.
How do we then link this data directly to the deploy time enforcement of binary authorization?
This is the expert-level integration. We just established that attester pipeline. That pipeline should be configured to only run the KMS signing step if the container analysis report confirms that the image has, say, 0 critical CVEs.
Or maybe 0 high-severity CVEs that don't have a patch available.
Right. You define your policy. But the security policy, 0 critical vulnerabilities, must directly dictate the creation of the attestation, the stamp. If the scan fails, the stamp is never applied, and BINOF will block the deployment downstream.
So container analysis provides the objective evidence, and the CI/CD pipeline acts as the judge and jury, deciding whether to issue the final cryptographically backed boarding pass.
Exactly. This proactive scanning saves so much time and effort. It prevents a compromised image from ever reaching the deployment gate in the first place.
That moves us perfectly into our second major pillar, managing the sensitive keys and secrets that the application needs to function once it's actually running. We need to talk about the vault. Okay, transitioning now to the runtime security component. So once the code is deemed trustworthy and it's running, how does it access databases, third-party APIs, and all those other sensitive credentials securely?
This is where we need to be really clear and distinguish between 2 critical specialized tools: Cloud Key Management Service, KMS, and Secret Manager.
They're often confused, but they serve entirely different security functions.
Entirely different. Understanding this distinction is key to professional security architecture. Let's start with KMS.
Cloud KMS, you said, is the locksmith.
It's the locksmith. Its primary role is not storing application secrets like API keys or passwords. Its role is storing and managing the cryptographic keys used for encryption and decryption operations. It's optimized for high-volume cryptographic work, key generation, and signing operations, like we just saw with BINOF.
Okay, so what's a specific CI/CD use case where using KMS for encryption rather than just storing the plaintext secret in a vault is the mandated secure method?
Imagine you need to incorporate sensitive configuration data or API tokens into a cloud build deployment. You never ever want the plaintext secret visible in your source code, your config files, or your build logs.
Of course not.
The secure solution is leveraging KMS for envelope encryption. You encrypt the secrets locally using a data encryption key, a DK. Then you encrypt the DK itself using a customer-managed key, a CMK, that's stored in Cloud KMS.
So you check the securely encrypted secret into source control, and it's basically useless to anyone who doesn't have the KMS key.
Precisely. You then include those encrypted secrets in your build configuration. You grant the Cloud Build Service account IAM access only to that specific keyring or crypto key in KMS.
And during the deployment?
During the deployment, the pipeline uses the key in KMS to decrypt the DK, which then decrypts the secret right before it's used. The plaintext secret only exists ephemerally in the build environment, and the key that does the decryption never leaves the secure boundaries of KMS.
That applies beautifully to data at rest, too, like sensitive backups.
Absolutely. Another strong use case is storing sensitive config files or compliance reports in cloud storage. Instead of relying on the default Google managed encryption, you ensure those files are encrypted using customer managed encryption keys, or CMEK, sourced from Cloud KMS.
And then you manage access to the key, not the bucket.
Exactly. You give the pipeline or the application IAM permission only to the KMS key via the cloud KMS.crypto key-to-crypto role, rather than giving broad read access to the storage bucket. This ensures that even if the storage bucket's security is breached or misconfigured, the secrets remain protected.
Okay, so if KMS is the locksmith that manages the tools, then Secret Manager is the actual vault that manages the contents.
That's the perfect way to put it. It's designed specifically for storing and accessing operational runtime secrets, API keys, database passwords, OAuth tokens, and crucially, handling frequent versioning and rotation.
For standard cloud-native apps, what's the simplest, most secure practice? Let's say an application on Cloud Run or GKE needs a third-party API key.
Simplicity is security. The most secure and simplest recommended practice is to save the API key in Secret Manager and then just reference that secret as an environment variable in the application configuration.
And the platform handles the rest.
The Cloud Run, or GKE infrastructure, handles the injection securely at startup. The secret never touches the disk or network in an insecure way. And your application code stays clean because it doesn't need custom logic for secret retrieval.
This is great for secrets that change, quarterly or annually, and you can do a standard redeploy. But what happens when that rotation schedule gets really aggressive?
This brings us to the advanced scenario that really differentiates the intermediate from the expert.
Let's lay it out. Imagine a highly compliant Cloud Run application. It connects to a legacy enterprise database, and due to some stringent regulatory rule, that database password must be rotated every 24 hours.
A common and painful requirement.
And here's the kicker. This rotation must occur with zero application downtime. No interruption.
This is the classic operational security challenge. If you rely on that standard environment variable method we just talked about, every time the password rotates in Secret Manager, what has to happen?
The Cloud Run instance needs a full redeploy, or at least a restart, to get the new environment variable value.
Right. And that action introduces downtime. It violates the zero downtime requirement, and it creates a huge operational burden.
So we need a deployment method that allows the application to dynamically absorb the new secret version without any interruption. What's the precise technical solution here?
The specialized solution is to leverage Secret Manager's dynamic integration capability. You store the password in Secret Manager, and then you mount the secret as a volume within the application's file system.
Okay, walk us through the mechanics. Why is volume mounting the key here, and how does it achieve zero downtime compared to environment variables?
When you mount a secret as a volume, it becomes accessible to the application not as a variable in memory, but as a file path, something like etc.secrets database password. The crucial difference is in the underlying mechanism.
What's the platform doing behind the scenes?
The Cloud Run infrastructure, or the agent managing the volume, is constantly monitoring the secret version in the cloud. When an authorized rotation updates the secret in Secret Manager, the infrastructure agent automatically and transparently updates the content of the file in the mounted volume.
On the running container.
On the running container, without requiring it to restart or redeploy.
So the secret is updated asynchronously to the application's lifecycle.
Exactly. The application code just has to be written to read this file's contents whenever it establishes a new database connection or refreshes a token, rather than only reading it once at startup. This enables the application to automatically access the latest version of the secret immediately after rotation.
Minimal downtime. It meets the requirement.
This capability makes volume mounting the mandated solution for any highly dynamic, high-rotation secret requirements.
That is a perfect, actionable distinction for our DevOps listeners.
Yeah.
Environment variables for static secrets. Volume mounting for dynamic, high-rotation secrets. We started this deep dive by declaring war on long-lived JSON keys. Now we need to tie this foundational principle back into the technical execution.
Right, closing the loop.
Let's revisit the mechanics that allow ephemeral environments, specifically GKE pods, to function securely and communicate with Google Cloud APIs without ever needing an exported JSON key. This is the implementation of Credential Zero.
This is workload identity. It's the core mechanism enabling this zero-trust ephemeral interaction. It allows GKE pods, maybe running Terraform or CI/CD agents, to gain the necessary temporary Google Cloud permissions by essentially impersonating a fully privileged Google Service account.
Impersonating it. Let's walk through that workflow.
Okay, so the process involves establishing a secure, auditable, and temporary trust link between the Kubernetes layer and the Google Cloud layer. When you're configuring a pipeline for, say, a Terraform deployment running inside GKE, you have to adhere to these key Google recommended practices.
Step 1. Define the identity inside the cluster.
First, you create a new Kubernetes Service Account, KSA. This is a Kubernetes resource, and you assign this KSA to the ephemeral pods running the Terraform job. This establishes its unique identity inside the GKE cluster.
Okay, that's the internal identity. Step 2. Define the permissions externally.
Second, you create a new Google Service Account, GSA, in your project, and you assign the appropriate least privilege IAM permissions to it. So the roles needed for Terraform to provision resources like compute.admin or storage.objectadmin, this GSA holds the real cloud access.
And the final critical step is forging the trusted bond between them.
The final step is using workload identity to map the KSA to the GSA. This mapping is an IAM policy binding on the GSA, and it specifies that the identity provider for that GKE cluster is allowed to authenticate as this GSA, but only if the request comes from that specific KSA.
So what happens when the pod starts up?
The pod uses the Kubernetes metadata service to generate a secure, short-lived token tied to its KSA. It then exchanges that token with the Google Cloud Security Token Service, the STS endpoint, for temporary Google Cloud credentials that are associated with the GSA.
So the pod is effectively swapping its internal Kubernetes credentials for temporary Google Cloud credentials.
Exactly. It can now perform the required actions without any static, vulnerable keys ever touching the cluster's file system. And if the job fails or completes, the ephemeral credential just expires.
And the lifetime is short.
Very short, which adheres to the principle of least time. Even if the token were somehow captured, it would be useless very quickly.
This principle isn't exclusive to Kubernetes, though. How does the same idea apply to, say, a traditional compute engine VM, like a dedicated Jenkins box?
The concept of using managed identities over exported keys is universal. For a traditional VM-based tool like Jenkins running on Compute Engine, the requirement is simpler, but just as critical. The Jenkins VM must have an attached service account with the appropriate least privilege IAM permissions.
And the VM gets credentials from the metadata server.
Right. The tooling inside the VM uses the standard Google SDK to query the metadata server to retrieve temporary, frequently rotating credentials associated with that attached service account. This eliminates the need to store static JSON keys on the VM's file system, which is a major risk for long-running infrastructure.
Workload identity and attached service accounts handle who gets access, but we still have to strictly enforce the principle of least privilege on what they can do.
Always.
So for a standard compute engine service account running an application, what are the bare minimum IAM permissions required just for basic logging and monitoring visibility?
You have to ensure the machine identity can only perform the right operations necessary for operational visibility and nothing more.
So to write application logs to cloud logging,
You grant the service account the logging.logwriter role.
and to write monitoring metrics to cloud monitoring.
You grant the monitoring.metricwriter role. These two roles are the absolute minimum for basic visibility, and they are purely write-only operations.
That separation is critical. Why is it so dangerous to just grant the editor role if the application is just running in a dev project? I mean, it seems easier.
It's a massive security debt. The editor role contains hundreds of permissions, including the ability to delete or modify almost any cloud resource. If an attacker compromises a machine with the editor role, they immediately gain control over resources far beyond what the application legitimately needs.
It turns a simple application exploit into a catastrophic infrastructure breach.
Exactly. By assigning only logwriter and metric writer, a compromise of the application only grants the attacker the ability to write garbage logs or metrics. That's a nuisance, not a catastrophe.
Okay, let's look at a common troubleshooting scenario. An application on a compute engine instance is producing logs, the ops agent is running, but the logs are not appearing in the cloud logging console. What's the primary expert level resolution?
If the agent is running and collecting logs locally, and you've confirmed network connectivity, the bottleneck is almost universally authorization. The primary resolution is adding or verifying the presence of the logging.logwriter role on the attached user-managed service account.
So it's an IAM problem.
It's a textbook example of IAM failing silently. Without that specific permission, the VM simply cannot execute the API call to push the collected log entries up to the centralized service.
That wraps up the identity for the machines themselves. But what about the data the machines are producing? We need to ensure sensitive data isn't leaking into our permanent audit trails.
Right. Before we even think about storing it long term.
We need to talk about the privacy filter. Shifting focus now to a security domain that I think is often overlooked, log governance and data sanitation.
It really is.
In our pursuit of complete operational visibility, we sometimes inadvertently risk exposing PII, personally identifiable information, in our operational records.
Absolutely. Security is about ingestion control just as much as it is access control and integrity. If PII or financial data gets captured in logs, that log repository immediately becomes a major compliance risk.
And it requires complex governance.
The best security practice is to never ingest it in the first place. We need an expert solution to handle PII scrubbing at the source.
Okay, let's get specific. A common problem. You have a web application on Compute Engine collecting logs via the ops agent. Through an application error PII, say, a data field containing the pattern user info or a credit card number is accidentally leaking into these log entries.
It happens.
You need to prevent this PII leakage into cloud logging, but compliance also dictates that you have to retain the raw original log entries in a secure, audited location for later incident review.
This is a complex dual requirement. Lock the PII from the mainstream, but retain the original data as auditable evidence. A simple exclusion filter in cloud logging won't work for this.
Why not?
If you only set up a log exclusion filter in cloud logging, the log entry has already been transmitted, ingested, and briefly processed by the cloud logging API. The PII has still crossed the compliance boundary. The most secure solution has to happen at the source, on the VM, before transmission.
So you have to leverage the processing capabilities of the ops agent itself.
Exactly. The ops agent uses Fluent or Fluent Bit for log parsing and filtering, and we use that.
We use a component within the agent to intercept and modify the log stream before it even hits the network.
We use a Fluent filter plugin within the ops agent configuration.
Yeah.
This plugin is highly flexible. You can use regular expressions or custom scripts to identify sensitive patterns like user info or IP addresses or credit card formats.
And what's the design pattern here? It's a two-step action, right?
It's a simultaneous two-step action. First, the filter is designed to match the sensitive pattern and concurrently copy those PII-containing entries in their original form to a secure, dedicated, highly restricted cloud storage bucket. This is our evidence locker.
Okay, so you save the evidence first.
Immediately after the copy operation, the same filter is configured to either completely remove the log entry from the primary stream or to redact the PII fields before the stream is sent over the network to cloud logging.
That is a massive distinction. We're using local processing on the VM to sanitize the stream before it even touches the organization's wider log infrastructure.
That's the key. By diverting the sensitive logs to a single restricted bucket, we compartmentalize the highest compliance risk. Source scrubbing via Fluent ensures only non-PII data enters the operational log stream, and that simplifies all of your downstream security and auditing burdens significantly.
Once logs are sanitized and streams are established, governance and access become paramount.
Especially in highly regulated environments.
So let's discuss the compliance requirement for long-term retention. If a company operates in a domain requiring 7 years of immutability for all audit and access logs across the entire organization, what's the best practice to minimize complexity and prevent accidental data loss?
And what's the operational overhead, right?
Exactly.
To manage this at the organizational level and ensure maximum safety, you have to use an aggregated sync at the organization level.
A single configuration point.
A single configuration point that exports all logs from all projects into a centralized archival location like cloud storage. And the critical security measure to prevent deletion or modification is enforcing that 7-year retention policy with bucket lock.
Bucket lock enforces worm. Write once, read many.
Correct. It creates a worm policy, making the retention policy completely immutable. Once it's set, no one, not even Google support or the organization administrator, can delete or modify those logs before the 7 years are up. It effectively takes the operational risk of accidental deletion right off the table.
Moving to IAM governance. If certain team members need the ability to configure these organization-level log exports, what is the least privileged role they require?
The ability to configure syncs and log exports requires the logging.configWriter IAM role. This is important. It grants configuration power, not data access power. They can manage the syncs without being able to read the logs themselves.
Now for the security team accessing the most sensitive logs. We need to grant them read-only access specifically to the data access audit logs, which are in that non-modifiable required bucket.
When dealing with audit logs, specificity is everything. You never grant a generalized viewer role. The precise role required for read-only access to those most restricted audit logs is roleslogging.privateLogViewer.
And you assign it to a group, not individuals.
Always. You assign it to a group containing the security team members. This ensures management is centralized, simplified, and auditable through the group membership.
Finally, let's address internal log segregation. All application logs from multiple projects are centralized into one logging project. How do we enforce a rule that each project team can only view their own logs, while the central operations team can still see everything?
This is a classic centralized logging challenge solved by layering access control on top of the centralized data. The optimal solution is log views.
How do they work?
In the central logging project, you create distinct log views for each project team. You apply filters that restrict the view to only show their specific application logs based on the source project ID or a log label. You then grant the development team access only to their specific log view.
And the central ops team?
The centralized operations team can be granted access to the comprehensive ALOGs view to retain complete organizational visibility. It's cost-effective, avoids data duplication, and strictly enforces data separation.
That covers the full spectrum.
Wow.
From preventing PII leakage at the source all the way to long-term compliance and least privilege access.
Today, we've completed a pretty extensive journey through the secure supply chain.
We really have.
We moved way beyond simple access decisions into depth integrity checks. We established that foundational principle of eliminating static credentials, which is the gateway to all of these secure automated processes.
We looked at the inspection station, binary authorization, as that final, non-negotiable gate for production integrity. We detailed the workflow for verifying the container image and its cryptographic signature, the attestation signed securely by workload identity and KMS.
And we solidified the requirements for runtime security. We differentiated Cloud KMS, the locksmith, from Secret Manager, the vault. And we highlighted that crucial requirement for dynamic volume mounting for zero downtime secret rotation.
A requirement dictated by stringent compliance.
That's right.
We then close by emphasizing credential zero with workload identity, showing how GKE pods can operate without static keys, and then detail the sophistication of the privacy filter using Fluent to sanitize PII at the source while meeting regulatory retention requirements with bucket lock.
The core security mindset for every engineer operating in this domain really has to be. We shift security left by scanning images early with container analysis. We find vulnerabilities before they can become deployment blockers. But we guarantee integrity at deploy time by verifying cryptographic signatures with binary authorization. We trust our development tools, but we verify their output before it ever touches production data.
And that brings us to the most powerful concept of the day for you, the listener, as you design your next secure pipeline. We discussed using container analysis to scan for CVEs, and separately, we discussed binary authorization for deploy time attestation.
The critical next step is integrating them.
Exactly. The attestation, that digital stamp that permits deployment, should only be applied after the container analysis report confirms zero critical CVEs, or whatever your policy is. Design your tester pipeline to fail the signing operation if the vulnerability scan fails.
Implementing that chain of trust, where scan results directly govern the ability to sign the artifact, that creates a fully automated, cryptographically enforced supply chain that guarantees integrity and adherence to security policy before any code is ever allowed into the live environment.
A powerful thought to end on. Implement that, and you've built a truly secure foundation. We'll see you next time on The Deep Dive.